So the end, yesterday I was telling you very quickly, maybe I want to say a little more about that. I was telling you that Wald constructed some very funny domains for 2 Bieber-Bach domains which are not Stein, which are not Runge, I'm sorry. Let me actually slightly sketch what Wald did. So basically he used the property so he proved two things, that there exists omega in C2, which is a for 2 Bieber-Bach domain. So it's biholomorphic to C2, but not equal to C2, such that omega is not Runge in C2. And of course, this can be done for any Cn n bigger than or equal to 2. And the second thing, you can use this domain later to construct X, which is a union of subdomains such that these are increasing these are domains, open sets in X, increasing, and such that each of them is actually biholomorphic to C2. But, so any such X would be called along C2. But of course, it may happen if you don't do this construction carefully that the long C2 is still the same as C2. In the end, it may happen that C2 would be, that X would be C2. But in fact, he constructed in such a way that X is not Stein. So in particular, X is not C2. And again, this you can do with any n instead of 2. So this solved a very old question. It was known before that, for example, there were constructions of John Eric Fornes from probably the 70s, that you can find such X, which is an increasing union of balls, for example, or polydiscs, such that at the end, this X is not Stein. But this was new. So here, the idea, I will not say too much about it, but the idea is this. So Wald used the property that we start with a manifold C star cross C. So it's a subset of C2. So you remove one line from C2. And then we know that this manifold has density property. Well, this one too, but we are interested in this one now. So this essentially means, this is the property I explained yesterday. This essentially means that any kind of holomorphic flow, which is defined globally, so you have a, let's say you have a vector field here on this manifold, holomorphic vector field, and you have a flow of it. Look at the flow. You can approximate the flow by automorphisms of this thing. But these automorphisms don't all extend to C2. And so then Wald found a submanifold, a very special one. In fact, it's just a disjoint union of two disks. So both Y1 and Y2 are embedded disks in C star cross C. So you have a disjoint union of two disks. Actually, they are totally real. Totally real means that, so the tangent plane to the disk, I mean the tangent plane to y at each point is not complex, it's a real. It's not a complex line. Such that it has the following crucial property, that if you take the polynomial hull of the set, so you take the hull with respect to polynomials on C2, this contains the origin. So in other words, the hull doesn't remain here, it goes out. It contains this point which is in the missing line here. But the hull of the same set with respect to functions which are holomorphic here, which means they can have also poles along the missing line. So the hull with respect to C star cross C is just the set itself. So this means that the set is actually, this union of two disks is what we say holomorphically convex in here, but in C2 it's not convex. And then the third property is that this Y can be squeezed to any small ball. So it's like homotopic to 0. So Y is null homotopic, but not just null homotopic, but I would say null isotopic in C star cross C. So this really means that I can squeeze Y. I have a family of smooth, even analytic deformations of this Y so that it ends up in a very small ball someplace. But during the isotopy, you still see two disks at each time, and these two disks still have this property. This property is lost, but this property remains. It stays convex at all times, holomorphically convex. Okay, so let's say that we have such a thing. This is the key point of the proof. But once you have such a thing, then you simply do the following. First, you take some map here from C2 to the subset, which is a Fatu-Bieberbach map. So first, there exists, this is well known from long ago, that there exists phi from C2 to a subset, let's say y to phi omega, which is in C star cross C, such that this map is biholomorphic. So this is a Fatu-Bieberbach domain, which omits one complex line, the line Z1 equal to 0. Well, and now what you do is you, okay, now you choose an isotopy Y sub t of this set Y. So you choose the squeezing, let's say when t goes from 0 to 1. And this is always staying inside C star cross C, such that, of course, yt hat with respect to functions on C star cross C remains y for each t. You start with your given one, say with this one. So y0 is y. But y such that y1 is small. In fact, you can put it into some little ball in here. So y1 you squeeze into this domain. Okay, and now we employ the density property. Now we employ the fact that all this motion, this isotopy, can be actually done approximately by automorphisms. So by density property of C star cross C, we can find a psi, let's say, which is an automorphism of C star cross C, such that psi of y is approximately equal to this y1. So it's, in any case, it's still contained in this big open set. So this is a compact subset contained in here. And now we just take, so this means if I now look at psi inverse applied to this, applied to phi. So this means y is contained in psi inverse composed phi of C2, which is again a Fatu-Bieberbach domain in C star cross C. Since I just applied to my previous Fatu-Bieberbach domain, I applied an automorphism, so it's still injective. So this is still a Fatu-Bieberbach domain. Contains y. Okay, so let's call this domain omega. And you see this omega now has the crucial property. So it's an FB domain. It contains the set Y. Recall that the polynomial hull of C2 contains 0. Okay? So this means in any case that it's not contained in omega. But this means omega is not Runge, because so omega is not Runge in C2. Because characterization of Runge domains, by omega of course is pseudo-convex, since it's anyway C2. Characterization of Runge domains is just that if you take any compact set in there, the hull, polynomial hull, has to also remain in it and be compact in it. This is not the case. Okay, so very simple idea. So that's for the first part. And then basically you just use this example and work a little more to get this thing. Because now, essentially to construct such a long thing, basically you will think of each such pair here to be more or less like this thing I made. So basically this will be a C2. And this map will be essentially my phi composed with psi inverse. So let's say you get a map phi1, you get phi2, phi3. So basically you just look at collection of maps like that. And each of these maps is essentially like one of these here. And then you just think of these maps as inclusions in some sense. So in the end, you construct your X by just saying, well, the points of X are essentially equivalence classes of points from here. So any point from here will be identified with its image point there, and so forth. And any point there will be identified with its image there, and so forth. So this is called inductive limit. And if you do this carefully enough, then you have the same phenomena as explained here. So basically here you get some compact set in the original copy such that the hull with respect to functions on X is not compact. And why is it not compact? Because you make it, the hull you make to go out of the image when you push it here. So you see the set here. Okay, but then the hull of the set here goes out of the image of phi1. And then you keep repeating this thing. So the image here, the image of the hull at this spot goes out of the image of phi2, and so forth. So this means that the hull at the end is actually not contained in any of these pieces which you get. But these pieces exhaust X, so it is non-compact. So this means this manifold is not Stein. I don't know, maybe one can do this a little better to even have no holomorphic functions on X. I think it's probably possible. So this was quite interesting. And then, since we are talking of foliations, let me state an improvement which I did. So Wald's result was published maybe last year. But I have a small improvement, which is the following result. So this is due to myself, and it's just now being published in the proceedings AMS. So this says I'm basically just improving his construction, adding some parameters. So I prove the following, that if S is any Stein manifold, you can think of S being as the unit disk. Even the unit disk is a good example. And then I take inside, I take two disjoint countable sets. Let's say A and B. So I take two disjoint countable sets, but they may be dense. In fact, that's the interesting case, when they are dense, each of them. Okay, then there exists a complex manifold X and a holomorphic submersion. So this means a map with surjective differential onto S such that first every fiber xs, which is a pi inverse of S for any point S of S, is along C2 or Cn if you like, but let's just say state it with C2. So any fiber of this map, which is smooth anyhow since this is submersion, so it's along C2, then I can arrange so that actually if I'm on this set, I have honest C2, so the fiber X over any point Aj is C2, an honest C2 for each Aj in A. However, xbj is non-Stein for every bj in B. So this means these fibers really change all the time, everywhere. So it's completely non-locally trivial. So it's a very funny foliation. It's a very funny complex manifold which is foliated by such long, trivially foliated by these fibers, by these long CNs or C2s, so that they keep switching from standard to non-standard all the time. It is not actually very difficult to prove this once you know what you're doing here. Basically, you see what you do is, so you use points in this S as parameter. And I said yesterday that anyhow, if you have density property, then you actually have lots of maps, lots of entire curves, but not just curves. You can, from any Stein manifold, you have maps from the Stein manifold to the automorphism group, holomorphic maps. And you can arrange those maps to have suitable properties. So for instance, if you're at this set, you try not to do very much, so that in this inductive limit, you follow this construction, but in this inductive limit, you will at the end get an honest C2. So you'll just sort of like keep repeating the same Fatu-Weber-Bach map. Then you start with one which is Runge. Here I didn't say, but the first map, here you can choose this one to be Runge. Okay, so if you keep repeating a Runge map, then at the end you'll just get a C2. But then when you go to points of this set, then you start doing these funny things which we did here. And of course, since we have countably many steps at our disposal, we can do it in such a way that at each finite step, you just satisfy some finite number of conditions. So on this set, on the first few points of this set, you do something. Here you do something else. And you have countably many steps, so in the end you can actually arrange some countable sets. Okay, so this was a recent application, but there have been many other older applications of this stuff. Perhaps I should mention of the older applications that right after the birth of this theory, of the Anderson-Lampert theory, I'm looking for the eraser. Dispari, il est dispari. How did you find it? I didn't see it. Of course, it's obvious. Yeah, an obvious place. Thank you. Okay, so let's mention some, just briefly, some other applications. One, there is a lot of work in algebraic geometry considering relations between embedded objects and automorphisms of the ambient space. Let's say if the ambient space is Euclidean space. So in particular, there is a very famous theorem of Abiancar and Mo. From mid-1970s, maybe 1975, or I'm not exactly sure of this year. Actually, it's also due to Suzuki. that if you take, if you embed C into C2 by a, so if this is a proper holomorphic embedding and if it's polynomial, so if this is a proper polynomial, so algebraic embedding, let's call it phi, then there actually exists an algebraic, let's say, an F, which is a algebraic automorphism of C2, which puts this line, so you get some embedded line, but then you can straighten it, so you can put this line back to the standard line, so such that F composed with phi of C2 of C is actually C cross 0. So we say that this line is straightenable. This issue has been studied in other dimensions too, but it's not completely understood. So for instance, I think if you polynomial embed C into C3, it's known to be holomorphically straightenable. So it's like here, except you have to put holomorphic here. But it's still not clear if it's algebraically, polynomially straightenable. But in any case, in 96, Rosé, Globevnik, and myself constructed, so in 96, sorry? Sorry? Hmm? This is polynomial automorphisms of C2. I just put algebraic here, but it's just PQ, just maps PQ where these are polynomials. This group is well understood, by the way. This group has been understood since 60 years ago. It's actually, this group is, yesterday I didn't say when I talked about the Anderson-Lampert theory, but if you talk about this group, this is Jung's theorem that actually it's generated by these shears, which I showed you yesterday, polynomial shears. But in C3 it's not true. In C3 it's not, it's a rather recent and difficult result that in C3 it's already, this group is not generated by those obvious maps. And in the holomorphic case, it was also a result of Anderson and Lampert that actually the shears we showed yesterday, we saw actually, I didn't say explicitly, but this theory which I explained yesterday shows that automorphisms which are generated by shears, that they generate a dense subgroup, but not everything. So there are automorphisms which are not shear, compositions of shears. But anyhow, in 96 we proved, so this was Globevnik, Rosé, and myself, that, and then there was actually another result by Buzzard and Forstnerič. So we actually proved that there exist properly embedded lines in C2, so proper holomorphic embeddings, such that, if I call it phi again, such that C2, such that it's not holomorphically straightenable, so not holomorphically straightenable. So what this means is that you cannot do this by any holomorphic automorphism. So there is no automorphism putting this line back to standard line. There is an open question in this direction whether you could make it twisted topologically, because this, in principle, this image could be a knot. I mean, smoothly you can easily do knots, so that the topology of the complement is not the same as, so the complement would not be homeomorphic to this complement. That's an open problem. But in fact, Buzzard and Forstnerič improved our construction and showed that even you can do this phi such that C2 minus phi of C can be hyperbolic in the sense of Kobayashi. So you see in algebraic geometry, it is known, and this was explained by Professor de Mailly, that if you take curves of high degree here, algebraic curves, but of high degree, so high genus, then this will typically not be it will typically be hyperbolic. But even with a line, you can do it if you twist it enough holomorphically. And there are similar results in higher dimensions. In fact, for any ck can be put into Cn in such a way that the complement is what's called Eisenmann n minus k hyperbolic. So it's very small, the complement, holomorphically. More recently, people put in disks. It's actually known, so this was Kuchenbauch and collaborators, that the unit disk can be embedded in C2 such that the complement is knotted. Also by these methods. So you embed the disk properly into C2 with a knotted complement. Actually, here it's funny that the problem, the open problem, is the opposite. It is not known if you can embed it unknottedly. And that's not too surprising, because to embed a disk is in any case difficult. C is trivially embedded already. Okay, so these were applications. Then there were other applications. For instance, this fact was used by Kuchenbauch and Dirksen. And this is also not too recent. I think it's around maybe 98. They show that you can construct automorphisms. In that case, they start. The first example they have is in C4, but then in higher dimensions also. So you can find out holomorphic automorphisms of C4, which are periodic. So this means some iterate is identity. Maybe they have some specific information of this number here. Which, however, is non-linearizable. So phi is not conjugate in this group to a linear one. And this was also an interesting construction, a log standing open problem. Because in many nice groups, you can, of course, you only have periodic things once you, all periodic are linearizable. But this group is really sort of unmanageable, very huge. Okay, so there are such results. So this has been very, and it's still quite an active area. But I don't wish to go too far here, because we have to anyway return to our main subject. So let's go back, and I have to explain you one more thing about, well, I still want to explain one more thing about automorphisms, because remember that in the construction, in the approximation theorem, for holomorphic submersions, from Cn to Cq with q bigger than 1 and less than n. So for q equal 1, we actually did everything. But for q bigger than 1, we didn't do everything, because then what was the problem? We have the following situation, that we have some compact set, convex. Let's put 0 inside. That's no loss of generality. So we have some compact convex set. And remember that in the first stage of the construction, so I had a submersion from a neighborhood of this set to CQ, and I want to approximate it by an entire one. And the first step was to approximate it by polynomial 1, but then I have to deal with this subvariety, which I think I called sigma, which is actually the critical locus of my polynomial submersion. So it's an algebraic subvariety. But the good point is that in these dimensions, its codimension of sigma in Cn is at least 2. So this means n minus the dimension, this is n minus the dimension of sigma is at least 2. So it's not a hypersurface, it's sort of thin. And what we have to understand is how to push it away. This I didn't really quite explain yet. Because you see, the goal was always that we push this away, almost leave this fixed, and then we are done, because then the inverse map, you look at notes from yesterday or 2 days ago, and you see the inverse map then puts a big ball into the space, into the complement of this variety. It's almost identity here, so that gives you an approximation. So basically the goal is to move this out of some large ball, the sigma, but not to touch k. I mean, not to move it very much. And this actually is not a straightforward consequence of the things which I presented. So if you want to understand this, you really have to study. So you must study holomorphic vector fields, or maybe, in fact, it suffices to study polynomial vector fields on Cn, which vanish on sigma. Why? Because then their flow. So essentially what you'd like to do is something like this. Let's say here I will take a radial vector field which contracts the set towards the origin. So let's say that on k, choose v to be minus some zj partial on zj. So it's just a contraction. Okay, so on k or near k. And then its flow is that tz is mapped to e to minus t times z. If you integrate this equation, you just get this flow. So you're contracting with this exponential factor. I'm just interested in the positive real time. So as time runs, you can squeeze it. But now I'd like to know if I can write this vector field. Of course, I can approximate. So the next step is approximate v by vector fields that vanish on sigma. Because what will the flow of such a field do? Well, the flow will then, of course, do the same thing here on k, but it's going to preserve sigma. So the flow will preserve sigma. Okay, let's call this flow phi t. So finally, you take E2 plus t times this flow as t goes to infinity. So what does this do? You see that on k, you just cancel this factor. So this is close to identity. Okay, but on sigma, it removes sigma to infinity. I mean, it sends it far away because you have identity for this map, but then you expand with this factor. So that's what you want to do. But you see, now comes the problem. You want to know if the density property still holds for vector fields like this, which vanish on sigma. And in fact, this is true, and this was proved by, let me at least show you that there are some vector fields which do that. So let's construct some vector fields which vanish on omega, on sigma. So basically, the theorem is which is due to Kaliman and Kuchebaugh. And it's a few years old, maybe, or 6 perhaps, I'm not sure. It says that the Lie algebra No, it doesn't say that. It says roughly this. So for every algebraic subvariety sigma in Cn with codimension sigma at least 2, there exists an integer n which depends on sigma, okay, such that every polynomial vector field V on Cn that vanishes on sigma, but not just to first order, but to this high order, vanishes to order n on sigma. And this means coefficient-wise. This just means that if you look at coefficients of this guy, they are polynomials, and you are just saying that these polynomials are in the ideal sheaf, in the ideal of sigma, but to the power n. Okay, so it vanishes, each coefficient vanishes to order n, at least on the subvariety. Each such thing is actually a Lie combination, so sum and brackets of complete fields in this class. So is a Lie combination so it's in the Lie algebra, it's a Lie combination of polynomial vector fields that vanish to order 1 on sigma. And that's precisely what we need. This is the theorem we need. Because if we have this theorem, then all of this, what I said here, can be done. Because you see, you start with this field on K, and then you, but just by standard theory, you can actually approximate it by a vector field that vanishes to as high order as you like on the sigma. And then you apply this theorem, and this theorem tells you that the flow of this field will actually be approximable by automorphisms which pointwise fix the sigma, right? So you fix this and you contract this. Okay, and that's so here you get automorphisms like this which shrink the set, leave this, and then you just expand back. So this means that that you actually have identity here and you push this variety off. Okay, so that's what they showed. It's as far as I understand, it's still an open question whether you can do this with n equal 1. They have some theorems where they do it with n equal 2 for in the smooth case, but in general, it seems it might depend on singularities of sigma. Which n do you need? But let me just say an idea. I will not prove this theorem because it's still again some algebra calculation, but what's the idea to construct vector fields, at least some vector fields, which vanish on sigma? It's very simple, actually. So here, imagine you have this sigma upstairs. So this is in Cn. And now you have many projections to Cn minus 1. So you have many linear projections from Cn to Cn minus 1, which are proper on when restricted to sigma. So sigma is mapped downstairs to some algebraic subvariety. Let's call it A. So there exist linear projections, many of them, P, from Cn to Cn minus 1, such that P restricted to sigma is proper. And this condition, of course, guarantees that the image is an algebraic subvariety. Is algebraic subvariety of Cn minus 1. But notice that it's proper. And why? It's just by dimension reasons. Here is where we need the dimension. This has dimension at most n minus 2. So once you project, it still has dimension n minus 2. And here you're in Cn minus 1. So it's a proper subvariety. And now it's easy, because now you just take the following vector field. So first you choose some vector in the vertical direction. So now we choose some vector v in Cn in the kernel of P. So some vector like this. And you also choose functions. You can choose functions, polynomials here, which vanish on A. So f, let polynomial on Cn, so it's a polynomial on Cn minus 1, and f restricted to A is 0. So choose such things, and then you can write the vector field f of P of z times vector v. Okay, this is a kind of vector field which we looked at yesterday. So it's a shear, right? It's f applied to the projection times constant vector, so it's a shear. So it's complete. And of course, by construction, v on sigma is 0, because sigma projects to the A, and f on A is 0. And you see, you can do this. You have many vector fields like this, because you are very free with choosing projection and choosing this f. So basically, what they did is to show that actually these vector fields, you have enough of them that you can decompose every guy that vanishes to some higher order into while using sums and lead brackets of these guys. So this is essentially the idea, and that completes the picture there. Okay. So let's stop about the subject and return to the proof now. Where do we stand at the proof of the theorem? So we did the key analytic part, actually. So we now return to the proof of theorem 2 or theorem 1. And these are theorems from the section 1. These are the main theorems, which I stated in the first hour, in the first lecture. So let's recall the sketch of proof. So we have a Stein manifold, and we exhaust it by some real smooth function, rho, which is a strongly plus supermonic. So rho is a strongly PSH exhaustion. So it means sublevel sets are compact. That's exhaustion. Strongly PSH means that, as I said, DDC of rho, the Levy form, so it's 2I DD bar of rho is everywhere strictly positive. And in local coordinates, this means in coordinates, this means that the Hessian of rho at any point z, the Hessian matrix, which is the matrix of second partial derivatives with respect to mixed variables. So once you differentiate with respect to, so this is a matrix with these entries. So you differentiate with respect to zi and zj. ij go from 1 to n. So this is 1 to n. This is called a complex Hessian. It's a Hermitian matrix, obviously. And this matrix is strictly positive definite. So it means all its eigenvalues, which are real, of course, since it's Hermitian, are strictly positive. So to this you associate the quadratic form, right? So you have a Levy form on a vector W, say, is just summation is just this quadratic Hermitian form. So this is strictly positive, except, of course, at the origin. Okay, so that's what we have. And there are many such functions. In addition, I will choose one further property of this function, namely that it's what's called Morse. I want it to be rho to be a Morse, which means that its critical points are quadratically non-degenerate. So this means the real Hessian, which is not, this is just a part of the Hessian. The real Hessian contains also some terms where you differentiate on twice on holomorphic variable and twice on anti-holomorphic. You actually have something whereby you take the real part of some similar thing, except that you have to take zi, zj here. So that's the other part of the Hessian, and then you have this. So the quadratic part at critical points I want to be non-degenerate. This will be important later. Okay, and if I start, I had theorems where K was a holomorphically convex set in X. And then you can always choose rho such that it's such that K is contained in rho less than 0, say, and this is contained in any open set containing K. So if you give me a small open set containing K, then I can always fit my rho in such a way that it's some level set will fall in between. Okay. So basically, I can assume that F is a submersion. So it's a holomorphic submersion on U. So it's let's say this is compactly contained. So I have it on some sub-level set. And now the goal is to extend it through level sets by approximation. So now the goal is to extend F by approximation each time. Of course, I can't extend. So I just mean each time I wish to approximate and make it holomorphic on a bigger set. And there are two cases which are very different from each other. So the first case, well, so basically the goal is like this. So we have two level sets. Let me draw them. So let's say here is rho equal to A. Here is rho equal to B. And my assumption always is that the submersion is already defined here on this. This is rho less than A. So it's defined on a neighborhood of this set, and I want to reach somehow this bigger set. I want to extend it to the rho less than B. Okay, so now we have two cases. And the case which more or less follows straightforwardly from what we did so far is the so-called non-critical case. And that's the case where rho has no critical points in between these two values in that annular region. So first case is the non-critical case. By the way, I can always assume that these two numbers, A and B, are chosen such that rho has no critical points on these levels precisely, because critical points are anyway isolated and go off. So I can always assume that there is nothing here exactly on these. But there can be in between. Okay, so the non-critical case is that differential of rho is nowhere 0 for each x in the set. Let me call the set XAB. So XAB is just the ring between. So it's the set of points X in X where A less or equal than rho of X less or equal than B. So it's this annular region. And the second case, which we'll consider, will be the critical case. So the critical case is opposite to this. There are some critical points. But actually, we can always choose. I didn't say this yet, but we can also arrange that critical points, different ones, are on different level sets of rho. That's easy, just small perturbation of rho. So that means I just have to treat the case where there is only one critical point in that ring. Because if there are several, then I just first approach the first one, then I have to tell you how I go over, and then I go to the next one with case 1, and then again go over, and so forth. So the critical case really is that there is exactly one critical point, let's say P of rho in this ring. But in fact, it will be in the interior, since I said that the levels are not critical. So the combination of these two cases will finish the proof, because you just do the usual induction. Then if you can do each of these steps, of course, you have to ensure that each time you approximate as close as you wish. Then in the limit, you will find the solution. By the way, I'm not telling you yet what happens if you have a subvariety. In my theorems, there was also a subvariety. But that's more analytically more complicated. So let's not go into that yet. You have to choose a different exhaustion then. So let's look at this main case. OK, let's start with case 1, the non-critical case. So case 1. OK, there is one key feature of such strongly superharmonic functions, and this is that, you see, basically, when you change coordinates, this Levy-form gets conjugated, but its eigenvalues actually don't change. I mean, you have so somehow this is the invariant part, in some sense, of the second order derivatives of the. And in fact, it's not hard to see that if you have a domain rho, if this is, let's say, level, if this is rho less than A, and this is the surface rho equal to A, well, I drew it too nicely. Perhaps it's complicated, but the theorem is, this is called Narasimhan's lemma, that for each point in the boundary, you can find a neighborhood in which this gets convexified. Here I drew it already as convex. So there exist local coordinates such that this part is convex. And in fact, you can even make it look like a ball, like a sphere. To second order, you can make it a sphere. And now what you do is you can attach to this thing a little bump. Now let me draw this picture better. So in local coordinates, let's say that, so basically you find some frame, such that your set here is complicated, but when it comes in here, it's going to be convex, like this. Okay, so I'm just looking at this piece within some window, and then you can bump it out, because it's strongly convex actually, so you can now bump it out. So that means you choose something a little larger. Let me, for simplicity, let me call this set A. So A is where rho is less or equal to A. And this is in X. But this is in, here we have local coordinates. So we can think that this box here is actually, we can think that this box is in Cn, okay? My manifold, the rest of this picture is not in Cn, but this is via some chart, it's in Cn. You can take some rectangle, and then you can add to this some kind of figure like this. Let me call this set B, such that B, of course, this level here is rho equal to A. Okay, and this, such a B, is again a convex set, strongly convex. And it's attached so that they have, I didn't draw very well, they share some boundary here. So basically, if you call this set C, then here the boundary of B actually coincides with the boundary of C on some part, and likewise here. So such a thing is called a bump. So B is a bump on A, or more precisely, you can call it a convex bump. So B is a convex bump on A. So basically, the property is that the union of these two things is still in the chart is still convex. So the key properties are that A union B, let's call it D, is still strongly convex inside my chart. So in this rectangle, the piece in this rectangle, which I think of as being in Cn, is still convex. The rest doesn't matter. B is convex. I also want this key property that the difference of these two sets, A minus B, so A minus B is what's below here, right? Okay, and then I intersect this with B minus A, and this is what's up here. These two sets don't meet because they are here separated by intersection. So this should be empty. Okay. So I said that I added a convex bump on my level set. But now it's a very simple geometric exercise. You can actually, the proof is written in chapter 5 of my book, that you can, with finitely many such bumps, when you add one bump, then you add maybe, you start with this as your new level, and you add the bump here, and then everywhere you can add bumps. And it's a simple exercise to show that actually by finitely many additions of bumps, which are of this kind, you can go from the smaller sublevel set to the bigger sublevel set in the non-critical case. Basically, you just use partition of unity and you add small negative things to rho, because adding negative thing to rho means that you really bump it out a little. So you have to do it carefully, but this is it. So the upshot is that all you have to do is to understand how will you deal with this situation. Namely, if I have a submersion on A, how do I extend it by approximation on A to A union B, to such a bump? But you see, this we basically know now. So okay, so we have F, which is a holomorphic submersion from an open neighborhood of A to CQ. This is what we have. But now I can use the theorem which I proved. Namely, I want a convex set in this chart, which is in Cn. And I know that I can approximate this F by some entire submersion, in particular by a submersion holomorphic on the whole chart, in particular holomorphic on B. So by what we proved, this was which theorem I forgot. It was theorem in the second section, no, in the third section, where I talked of Anderson-Lampert theory. So by what we proved in section 3, we can approximate F restricted to, of course, A intersected with this. Let me call this something. Let's call this box P, for example. So let's say that P is this box. It's a rectangle. So we can approximate F restricted to P intersection A by a holomorphic submersion, let's call it G, defined in a neighborhood of the set B. Okay, so I have now two competing things. They don't exactly match, but they're close. So this means F and G are very close. So F and G are arbitrarily close, uniformly close on some open neighborhood of C, which is A intersection B. So on this set here, on this set here, they're close. Okay, and now, so now the first thing we do now is to actually show that we claim, and this is easy to see, I'll give you a hint. We claim that there exists gamma, which is a biholomorphic map in a neighborhood of C, and which is very close to identity map. So it's just like small perturbation of identity. In fact, since we are in Cn, I can use local coordinates. Let's say that local coordinates here are Z1 up to Zn. So basically, I can write a gamma of Z as Z plus some little c of Z, where this is very small, holomorphic. So it's just a small perturbation of identity such that F is equal to G compose this gamma such that this equation holds near C. When I say near C, I mean in some neighborhood. Each time you have to shrink a little. You do several steps, each time I shrink. But anyway, I have this. So this I call transition map. Of course, if F and G were biholomorphic, then this is obvious, because you would just take gamma to be G inverse F. But they are not biholomorphic. But the idea for this is really simple. Namely, think of level sets. Let's say here is level set F equal to something. And then I have a level set G is equal to the same thing, and they are close. And these level sets are smooth. So level sets of F and G, and I'm just looking at the neighborhood of this set, are smooth submanifolds and close to each other. But there is one other thing, that namely, so I have foliation by levels of F. But remember that this foliation has trivial normal bundle, because the foliation, the normal bundle is essentially just defined by differentials of the components of F. So basically, in this normal direction, we have trivial. So what I can do is I can set up easily a holomorphic foliation, a flow of some vector fields, which is transverse to the foliation of F, and therefore also transverse to G. So this is some transverse foliation, and I can choose it to be of complementary dimension. So actually, the leaves of F and the leaves of this foliation intersect at points locally. But now it's rather obvious what I do. I mean, for this point, from this point, I have to move to this point, right? So the same horizontal leaf, which if I'm at X, or let's say Z, okay, then the same leaf will cut the level set of G somewhere here, and I call this point gamma Z, and I have uniqueness. So this is my map gamma. That's essentially, this is implicit function theorem if you do this properly. And so this means F z has the same value as g at gamma z. Okay, so that's how I find gamma. So that's the easy part. And now comes the, now let me go to the other board. Now comes the slightly more difficult part. Today I finish at 11, right? Okay. So the so second part, and this is the what I call a splitting lemma. Is that I can decompose gamma as follows. So given gamma, so the precise statement is you're on some fixed neighborhood of C, which is, in fact, this can work anytime you have strongly pseudo-convex sets, like in my picture. So I'm on some fixed open neighborhood. And if gamma is close enough to identity on that fixed open neighborhood, then I can split it like this, where alpha is close to identity on a neighborhood of A. So this means alpha is a biholomorphic map defined on a neighborhood of A. And it's close to identity. And actually, this, you can control the distance of alpha to identity by the distance of gamma to identity. And likewise, beta is a similar thing on a neighborhood of B. So basically, I'm splitting it compositionally, these two things. It's a compositional splitting of a perturbation of identity into two pieces, left and right. Of course, here you have to be careful. Neighborhoods, due to composition and inverse, neighborhoods will shrink. So you have to have gamma on a little bigger neighborhood, and then you'll get alpha and beta on slightly smaller neighborhoods, but you will anyhow have estimates. There will be some constant, and you will have estimates estimating the distances by some constant times the distance of gamma to identity. So you have estimates the distance alpha to identity is controlled by distance of gamma to identity, but you have to choose good neighborhoods here. So let's say you have some neighborhood here, you'll get some neighborhood there, and likewise for beta. So there is some constant in between. Okay, let's say that we believe this lemma for the moment. This is like some kind of Cousin problem, right? Except the difference is that in a usual Cousin problem, you just want to decompose a map as a difference. And that's not good enough for me here. If I just try to do it, I mean, naively, you might say, okay, how am I going to glue? What's my purpose there? My purpose is to glue F and G. But the usual method of gluing is that you look at the difference, which is small, and then you solve a Cousin problem. So you write this small difference as a difference of two things, one on the left, one on the right, and then you just subtract. But you see, that's not good enough because you're going to, in general, introduce new critical points in this way. If you just do it this naive way, I tried and it didn't work. So that naive approach doesn't work. But what we do instead is do this splitting. And now the last step is obvious, right? Because now what we have is on a neighborhood of C, we have that F is equal to G compose this transition map, but this map I have written like that. So it's G composed beta composed alpha inverse. And now we put alpha inverse there, so we write this as F composed alpha is G composed beta. And now we observe that this guy, so this is a biholomorphism close to identity, and this guy is a submersion. So the result is still a submersion, which is close to F. So this is a submersion near A, and it's close to F. While this guy is also, by the same reason, it's a submersion, since it's a biholomorphism composed with a submersion. So this is a submersion near B, and it's close to G. And this holds on the intersection. This holds near C. So it means the two sides together just amalgamate. So you have a solution now. If you call the solution F tilde, then you have a submersion. So this gives a new submersion F tilde on a neighborhood of A union B. Actually, these are closed. Okay. And so you can keep going. Okay, so that's how we do this. This lemma is not very difficult to prove. Let's see. I don't have too much time now, so I'm not going to prove it in detail, but let me just say a few words what you do there. Basically, you still use the Cousin problem, but then you have to iterate. So it's some kind of Nash-Moser iteration. It's just the expected thing. So the idea of proof of the splitting lemma is that you have gamma, which is z plus some small function of z. And this is defined near C, near the set capital C. Okay, now you split, first you split C in a difference, B minus A, where A or B are small, and this one is defined near capital A, and this one is defined near capital B. Okay, and this is just Cousin 1 problem. So here you just solve it by using Debye problem, actually. So you said this is a usual Debye problem, and you know that you're in a strongly pseudo-convex domain, so you have a bounded solution operator for Debye on many nice function spaces. You can use even functions that are continuous up to the boundary of some strongly pseudo-convex domain and holomorphic inside, or some Hilder space. And so you get this decomposition. And here the norms of A and B are bounded by the norm of C. So you get that norm of A and norm of B are controlled up to some constant by the norm of C. Again, you have to take suitable sets on which this holds. And now you simply define new maps. So you define alpha like this and beta like this. But this is not the solution yet, so I should use maybe other letters, but you'll see the idea. So you define these maps, and now you define a new map as follows. You just take beta inverse gamma alpha. So you look at this composition, and this turns out to be, okay, what we would want is that this is identity. If I have solutions, then this would be identity. But if you just do this naive thing, this is not identity. However, it's something like this again. It's close to identity. And this I call error term. So it's a map of the same kind. But now the good point is that the error can be estimated by, basically, I'll write now more precisely. So let's say that I will denote by A sub R an R neighborhood of A. This means I take some metric, and in that metric, I use a neighborhood of radius R. Okay, just push out a little. So now I have a rather precise statement here that if I shrink C by some number delta, if I increase it by R but then shrink by some number delta, then I can control this new error by some universal constant, m, some constant. This constant only depends on the geometry, times epsilon square divided by delta, where actually epsilon is the norm of the previous function on this neighborhood. So basically, I have the previous error is epsilon. The new error, and I have to shrink for some amount, delta, will be bounded by epsilon squared divided by delta. So what's good is to have epsilon squared here. What's bad is to have this delta. But you know, that's usually in the iterative process, because now you continue, and you can actually pick easily sequences of deltas and epsilons such that deltas give you, in the end, limited amount of shrinking. Let's say that all the deltas will add up to 1/2 of r. So you shrink from R neighborhood to R over 2 neighborhood. However, you pick up epsilons much smaller than deltas in such a way that this sequence, epsilon square divided by delta j, goes to 0. So in fact, you will only find the solution in infinitely many iterations. But okay, this is what happens at each step. And again, I won't go into the details of this. It's just some calculus. Sometimes this is called Nash-Moser type iteration. You really cannot have it as an implicit function theorem. It's just okay. And then you're done with a non-critical case. So that's case 1. Okay, and then you have to understand what happens in case 2, which is the critical case. So case 2, start here. Well, again, you can look in local coordinates, because you just have to understand what happens. So here we can be in coordinates. We can just choose some local holomorphic coordinates near a critical point. So I can assume that this critical point, let's say, P is 0 in Cn. So this means derivative of rho at P is 0. We can also assume, to simplify, that rho of 0 is 0. Just to simplify, subtract a constant. So basically, as you know, critical points look like this. You have these separatrices. So the level of rho through the critical point is something singular. If you're below the critical point, you have this nice level set, sublevel set. So this is rho less than some negative constant. Then this up to here is where rho is less than 0. And if you go above, then you get rho less than, say, plus c. Okay, so it's this change. And you see that topologically speaking, the change is given by actually just taking some sublevel set and gluing to it a disk. And this disk is precisely the disk in the spanned by eigenvectors in the negative eigenvalue directions for the Levy form of rho. So you have such a disk. And if you glue to this sublevel set this disk, then what you have above can be shrunk, topologically shrunk on this union of the disk with this, we call this handle. Let's call this handle E. Okay, now to do anything, really, we have to understand more precisely how do critical points look like. And here I will actually write for you the normal form. And when I was writing my book, I first thought that this was, I gave some references, but then a colleague of mine pointed out that in fact this normal form has been known since, let me find the reference, since 1924, you wouldn't believe. So a certain Japanese called Takagi in 1924 proved the following normal form. So what does normal form mean? I just mean that you choose coordinates correctly. So you take biholomorphic changes of coordinates at 0, in which rho at the critical point will look like this. Okay, let me find it now. Okay, so it looks like this. So it's minus, I'll just write and then I explain the notation. Minus x prime square plus x double prime square plus sum j equal 1 to n lambda j yj square, where x are the real parts, so each zj is xj plus iyj. X prime is the first finitely many x's. X double prime are the remaining x's. Lambda j are some eigenvalues. Okay, here I need a little remainder too, in general. And in fact, these eigenvalues are such that lambda j, first, what is k? K is the number of minuses you have here, and this is the index. So k is the what's called the Morse index of rho at 0, the number of negative eigenvalues. All the other directions are positive. And these numbers lambda j are bigger than 1 for those j's which correspond to the first k axis. So for j is 1 to k. And then they are just bigger or equal to 1 for the rest. For j is k plus 1 to n. And this has to be so, because if you calculate the Hessian, you see that it's essentially just, we have decoupled equation, so it's just Laplacians in individual complex variables. And if you calculate the Laplacian of minus x squared plus lambda y squared, you get 2 times lambda minus 1. So lambda has to be bigger than 1 in order for the Laplacian to be positive. But in this case, where it's positive, you don't have any condition, but you can still get it bigger than or equal to 1. So this is the normal form. And then it's also easy to see that by small adjusting of rho, we can actually kill this term. This is not by change of coordinates, but by just sticking in some cutoff function here. So you don't need to consider this term. Okay, so that's the situation. And the handle here, this E, is in this x prime direction. So the coordinates are that here it's x prime, and all other coordinates are there. Okay, so you see that k has to be, in any case, k has to be less than or equal to n, as I said at the beginning. Okay. And now what you do is, so what are you faced with? You have a submersion already on this set up to here, which I shaded on this set, or in some neighborhood of this set. And you can come as close as you like to the problem. And in the first step, I'm going to try, I will try to extend my submersion just smoothly first to the handle E. So first, extend F, which is a submersion on rho less than or equal to minus C, for some C less than 0, C positive. Across the K disk E. And this disk is totally real. It lies in the real space. But how? Okay, so that I have the maximal rank condition, so that the rank of the matrix of, okay, F is a map to CQ, so it has Q components, so I take derivatives of its components with respect to now the real variables on this disk. Yeah. Okay, so I wish the rank of this matrix to be full, to be equal to Q. Well, actually, let me deal, there is a little complication here. Let me deal with the case, actually the worst case is where K is equal to N. Where K is smaller than N, then I actually, when I do this, what I'm about to explain, if this handle is small, then I add to it some transverse piece, and actually I extend across that transverse piece too. So I'm just going to look at the case, look at the worst case. So this is anyhow the worst case. So let's just put N here. Otherwise, there are some further technicalities which I don't want to go into. Okay, so I want the rank of this map to be Q. So it's maximum. So here I'm just dealing with real variables, you see. Okay, but can I do this? Well, so what should this be, really? So this means that this matrix is really Jacobian matrix in the real variables should lie in the space of Q by N matrices with complex entries, the space of all Q by, which is just CQ times N, but then minus a set, let's call that set sigma, which are matrices of non-maximal rank. And we already looked at such a variety, and we saw, I gave you an argument last time, that this sigma is an algebraic subvariety of codimension, complex codimension is n minus q plus 1. Remember this argument, you just look at minors. You look at how many equations you need in order to say that you have less than maximal rank. Okay, so you see now if n, which is the number of these variables here, which is the dimension of the handle, is less than the real codimension of this, so twice the real codimension of sigma, which is of course twice this number, then such an extension, and I'm looking for a smooth extension. I didn't say here, but just I want to smoothly extend F, smooth extension. Such a smooth extension exists just by transversality theorem, by Thom's jet transversality. Because what does transversality theorem say? It says that if you look at a map from some manifold to some other manifold, then most maps will be transverse to some given submanifold there. But also if you take the jet extension, like the first derivatives, and if in the space of first derivatives you have some obstacle, and if this obstacle is small, meaning that it's a submanifold or subvariety such that the sum of the two dimensions is too small, then the only way that such a map can be transverse, so Thom's theorem says that its generic map F will, the first jet will be transverse to the sigma. The only way it can be transverse to sigma is that it avoids it just because n is too small. So n plus the dimension are less than the ambient dimension. Okay, and if you look at this equation, so you see that this works if n is less than 2n minus 2q plus 1. So this gives me n here. So 2q should be 2q should be less than n plus 1, which means q should be less or equal than n plus 1 over 2. I hope you remember this number. This was the number where I gave you a theorem without any conditions. Yes, I'm over time, so I'll finish. Well, let me just say what we do in the other case. So in this case, you can extend it, and that's it. Well, but then you're not quite done. But then the rest is just some simple analysis, because once you extend it smoothly, and this is totally real, then you can use Mergelian's theorem. You fix the jet in the other direction so that this map F, which is smooth here, extends to an almost holomorphic map, to a map whose d bar vanishes to any order you like on this piece, E. So you extend it in the other variables, so the d bar vanishes to as high order as you like here. Here it's anyway holomorphic. And then by using, again, d bar problem, you can approximate it by something holomorphic in such tube. And then there is some more geometry to do in order to show that once you're in the neighborhood of this set, together with this some tube around this handle, then you can keep going by the previous method, the so-called non-critical case. You can just keep going higher then. That's still not completely trivial, but it's just some geometry. So basically, you see that going across the handle, in this case, it's easy. But now comes the other case, where you have a H principle. So if this is not true, this inequality, well, in such case, you have to use this some theorem of Gromov, which says essentially that, see, in the other case, we had some 1 forms which did that. So basically, those 1 forms give a solution, so a map from your handle to here, but you don't know that those forms, they're non-integrable. So it's a non-holonomic solution. It's just some topological solution. But Gromov tells you that for certain kinds of differential relations, and this one is easily to be seen to be one of those, his condition is to be so-called ample in coordinate directions, which again would take some time to explain. So his theorem, which is actually an old theorem from Gromov's PhD thesis, is that if you have such a relation, then you can change any topological solution to an honest solution, meaning that if you just have some funny forms here, you can change those forms without doing anything on the boundary of your E where it's already good. You can change them to some differentials of functions. So basically, Gromov tells you that, yes, you can do this again. That stuff was actually, it predates Gromov, that lemma, but it was essentially developed in by Smale and Hirsch for the theory of emergence. So the so-called H principle for emergence rests on the same principles. Later it was used for smooth submergence, and now we use it quite a lot in the holomorphic geometry, using these tricks that first you use the smooth principle, then you extend almost holomorphically, and then you use some analysis to approximate, and then you go. So that's basically modulo these details, which I didn't say, would be the end of the proof. And I'm 5 minutes over, so that's a good time to stop. I should just say before I stop that there are actually still a lot of open problems in this. Let me, if you allow me 1 minute, it won't be 10, really, just one. Just one. Okay, one open problem I have already indicated, and that's that this theorem doesn't work for in the top dimension, but it's not topology that's the issue. That's the issue, but it's the analysis. Remember that we could not approximate locally by holomorphic maps of Cn by maps on bigger sets. That's one problem. But there is a more challenging problem which is not of that kind. So, okay, suppose I have this situation. I have a few differentials. So let's say that this is non-zero. So I have some holomorphic functions which have linearly independent differentials, like we have been constructing. Now suppose that I have an additional 1-0 form, so that this is also non-zero. So this is just some non-integrable 1-0 form. Okay, the question is, can you change this to the next differential? by always keeping this condition. Okay, this I don't know even in simple cases. So what would this geometrically mean? You see, each of these defines a hypersurface foliation, and this condition is that these foliations are transverse to each other. And then I'm asking, if there is no topological obstruction to having one more foliation transverse to all the previous ones, is there really one? The problem is that on each leaf, you can of course do it by existing theory. So you have your foliation with leaves, and on each leaf you can find your next non-critical function, so that would be fine. But then I have no way, I don't know how to patch when I go from leaf to leaf. So in the simplest case, this would say, let's say that I foliate by curves, okay? Now on each curve I know how to find a non-critical function, but how to find one that's non-critical on all leaves? Okay, that's sort of a problem. Okay, now I really stop. Was it 1 minute or 2? Maybe.